Hello everyone. So it's really my honor to be here. This is a very beautiful place, and also the top universities, not only in Korea, but South Korea, but in the whole world. So I see the KAIST University is comparable to the position like the Tsinghua University in China, which is the best. So I'm very glad to have this chance to communicate with you guys, which are all the best like transportation scholars and students in the whole country and in the world. Okay, so today I'd like to talk about some of my research ideas. It's about the new opportunities in traffic operation and safety research from the trajectory level perspective. So this is, I think, is not a presentation for one research article. It's actually the story about my past like 5 to 10 years, how I find out some research ideas, how I try to seek for some new opportunities, trying to seek for some new ideas, and what I finally did in the past years. Okay, so this is the outline of my presentation. So firstly, I want to have a brief introduction. I come from Southeast University. I'll have some formalities. Okay, so it is, unlike KAIST, it's not the best in China. It's, I think, ranking around 10 to 20. But the transportation program, I think, is the best in China. So you're all welcome to Southeast University and the School of Transportation for visiting and for communication. So this is my personal introduction. So mainly I focused on the ITS, traffic flow theory, which I learned from KIT, traffic safety analysis, and like intelligent, connected, and autonomous vehicles control. Okay, so why was I invited? So I think just as KIT introduced, I know several South Korean scholars, like the KIT Zibin Li. I think he's also in KAIST, right? Ku Hong Chung, who directed me like in research when I was in Berkeley. He came. Okay, I know him from the Southeast Monash program. I never been in South Korea, but I like watching South Korean movies. Okay, it's really interesting and good, different from the societies in China. Okay, so that's why I was invited. So thanks a lot for this great opportunity. Okay, so let's go to the technical part. You see, we all in the area of traffic engineering, and the purpose of the traffic engineering is to design, manage, and control the traffic flow for the efficient and safe transportation, right? So to achieve such goal, we need accurate traffic models, okay? For one part, we need the models to describe the traffic characteristics, and for the other hand, we need the models to evaluate the performance of the traffic. So that's why. Okay, that's why we need the data in the traffic research. Actually, data is very important. In transportation research because our discipline is essentially an empirical discipline, supported by the data. Okay, so we need the data to understand the traffic patterns, to evaluate the interventions and for the safety analysis, right? So in the early stage, when I was a graduate student, the major method to get the data is to do the household survey. So we send a lot of questionnaires, and we conduct a lot of on-site we call counting experiment, right? So we collect some data, and then we use some develop some method by this data to analyze the results. But such kind of method is, the data is very rough and like continuous sampling. We just randomly ask people to answer the questions. Then later, so we have the long-term static traffic data for analysis. So that's what I got when I was a PhD student. So for example, we have the accident data, we have the road design data, weather condition data, traffic volume data. That's all static data accumulated in a long term. So with that kind of data, we can do some modeling work, trying to see the relationship between the factors. Actually, the challenge within the long-term statistic data is they can be difficult to accumulate. So it takes a long time to get this data, usually several years, right? So it may not capture the short-term dynamics of traffic information, right? Then with advanced information technology, so now we have a lot of data source for us in the transportation field, like the cell communication data, parking data, ETC data, things like that, right? So it's in the big data era. In this big data era, so the main modeling logic is using the machine learning methods. So I think you all have the experience using the machine learning method. You know, in this kind of method, you need to train the model with a larger number of samples. Then you can directly get the results from the output of those models, right? So accuracy is really high. However, those kind of models, they perform like a black box. You can infer some variable influence by the sensitivity analysis. However, you never know why this relationship happens in this kind of model, right? So don't know the reasons behind those effects. So this kind of research is okay for studies focusing on the results, like the congestion prediction, demand forecasting, and event detection. Actually, I conduct a lot of research using the machine learning methods, okay, and I published some articles. However, so if I want to go deeper, I find out that this kind of method is not okay for studies that focus on the causality analysis. For example, like the safety analysis, accident prevention, like cause of congestion. So machine learning cannot give you the answer to those kind of questions. So that's for the methodology part, okay? So we actually need some kind of way help us to know the causality in the transportation field. Okay, so this is an example of why the causal analysis is so important. So I think when I was an undergraduate student, if people ask me why traffic congestion occur on expressways, I think the answer will be it is due to a lot of vehicles on the road, right? But if you are a graduate student, actually you have more knowledge about the traffic flow. So why there's a congestion? It's not because of a lot of vehicles, because it's a balance between the capacity and the volume. So you will say because there's a bottleneck ahead. Without bottleneck, there will be no congestion on any road. So there's a congestion because there's a bottleneck with reduced capacity, right? So that's an answer for the graduate student. But that's not enough. If you are a PhD, I think you will ask more and deeper questions like what triggers congestion? What factors influence the severity of the congestion? A lot of questions like that. I think those kind of answers require the deep and causal analysis. Okay, so that's the summarization of the traffic flow series in different areas. You see, we actually the methodology can be summarized into 4 different years, different stage. Like initially the probability theory, the mathematical formula stage, aggregated data stage, and the trajectory data stage. Okay, in each stage we have different types of method. For example, like the probabilistic methods for traffic flow. Actually, we set up several distributions to describe the traffic system. And actually, no data is required. It's just the formula. You give the input, you will get the output, right? Then the numerical method like the traffic flow models in the early stage. So we need to calibrate it with very limited data, like this one, green shield. He proposed the fundamental diagram, okay? But this diagram is only based on very limited data, okay? So aggregate data traffic flow measures, okay? So I think when I was in Berkeley 10 years ago, I mainly conducted research based on this kind of data. It is with large amount of discrete data. We have a lot of many famous systems that can provide this kind of data, like California PAMS system, Washington GeoNet system, like something like that. You know, this is the PAMS system developed by the Berkeley and the Caltrans. So you can see they have the loop detector on every freeway in California. You know, the distance between two detectors, I think, is on average 1 mile. 1 mile. So you can download all the detected data on. You can select the date, select the time, and you can download the data on each lane, each travel lane, the flow, speed, occupancy, the data. Okay. So with that kind of data, you can conduct the research. For example, this is the congestion pattern on the freeway. So you can see they have a time axis, so you can see what is the initial location the congestion started, and what's the evolution feature. Okay. So you know, those are some data. Okay. So when before I go to Berkeley, I have no idea about my research. I have no paper. Okay, I was very nervous, but I don't find a way. But when I go to Berkeley, I talk to Kitty. He told me, oh, you can always look for this kind of data. Okay, so I get this data. It's really amazing data. So actually, this data saved my academic career. So based on this data, I write a lot of articles. So my academic career is alive. So this is some example I conducted based on the highway traffic detector and accident data. So I actually like this one. So we developed a surrogate safety measure for evaluating the collision risks to the kinematic waves. Okay, like this one is a collaboration with Michael Cassidy, collisions in freeway traffic, the influence of downstream queue, and interim means to address them. Okay, so those are all based on the detected data. You see, the feature of the detected data is we have outputs, a lane-based speed, flow, occupancy every 30 seconds per 1 mile. That's the data I get. Okay, but after I do a lot of research, then I find out that there are some limitations with this aggregated data, because it is only at the discrete fixed locations. It only allows for the aggregation of traffic flow data for certain sessions. Okay, so it cannot actually identify the real-time vehicle driving status. We don't know what's the status between two detectors. Okay. So it also cannot reveal the risk mechanisms, because we only have the detected data. We don't know why two vehicles have the collision with each other. Then I think the the data is important to do, if you want to go deeper. Okay, so we have different types of trajectory data, like the mobile signaling data, the GPS trajectory data. But I think a lot of researchers use this kind of data for research purpose, and you can see they published a lot of great articles. But from my point of view, I think we actually need the trajectory data for all the vehicles to analyze the cause for the traffic problems. Okay, so then comes to the topic why the trajectory data is so important. So the most famous trajectory data is next generation simulation data, the NGSIM data. Okay, it's also very famous. It contains the trajectory of all vehicles, the high resolution. The data is per 0.1 seconds, the 0.01 meter. Okay, the resolution is very high. This is the trajectory. You can see all the traffic phenomena in this trajectory data. This is my friend. You see, actually, he has a review article summarized the research that are conducted based on the NGSIM data. You can see, up to 2017, there are more than 200 articles based on the NGSIM data. Okay, more than 100 published in the Part B and Part C. Okay, so I think this review article is recommended if you have interest. They summarize all the research in this field. Okay, but the NGSIM data still have the limitation if I want to conduct more research, because it only have the in this data they have the cameras, fixed cameras on the roadside like a building to get this data. But you see a lot of researchers trying to validate the accuracy of this data. You see, this research gets the conclusion that the errors cannot be corrected through the post-processing algorithms. Also the limitation, the inaccurate data, limited spatial temporal coverage. They only have data at 4 locations. Limited coverage of traffic condition. Limited diversity of the data collection roads, only on 2 freeway, 2 urban road with limited geometric design. Limited variety of traffic compositions, right? So if we want to conduct a research based on the trajectory data, so I think we need a new method to get those data, right? So why NGSIM data is not good? Why we need to get the data for all vehicles in a variety of scenarios? I think because it is really not good if you say I developed some models, but this model only works for the flow rate of 1,000 vehicles per hour, right? I have some good features, but only works for merging area with 200 acceleration rate. Actually, we want the data to cover all the scenarios, right? So that's the the initial idea in my mind. Why I then transfer my research to this, in extracting the trajectory data from the unmanned aerial vehicle flying above the roadway. Okay. So actually, when I was a postdoc researcher in the University of Washington in the Star Lab, which is very famous in the ITS field. My supervisor is Yinhai Wang. So actually in the group, I see they are doing some good method for the image processing. Then at that time, I know this kind of method can be used to get the trajectory data. So with the new data, we can do a lot of new research, right? So then I transfer my research to how to extract the data from the drone videos, right? So you see, so now we have the drones. It's very easy to fly on the road, right? So it can take the video at any time, any location, in any traffic condition, right? So we don't need to install the cameras on the building, right? We can just collect any data we want, but we still have some challenge if we want to do the thing, like the low resolution, low pixel vehicle in the image, like the shaking of the drone, right? So that's why we then conduct some research. We try to extract the data. So in the initial research, we try to extract microscopic traffic flow parameters. Then we have some research like this one. we have the real-time detection of bidirectional traffic parameters based on optical flow and feature clustering. At that time, we don't have the deep learning model. We don't have the YOLO series. Okay, we just at that time we just want to how can we get the data? Then we use the optical flow to detect the feature points on the moving targets, and then we use the feature clustering to make them into different groups. You see, they travel at different directions, and also those are some points belongs to the background. Some points belong to the vehicle in this direction. Some belong to the vehicle in that direction. By using the clustering, so they can be separated. Okay, so that's the initial research in 2016. Then we trained the model with some data using the convolutional neural network classifiers, trying to detect the traffic parameters. Okay, at that time, we just extracted the speed, average speed, flow rate, occupancy density, the microscopic traffic flow parameters. Then we started tracking the trajectories from the videos. So we have different types of methodologies. For example, we have some trajectory extraction method based on the detection and the tracking. The trajectory extraction purely based on the deep learning. And also we have some research to deal with the multidimensional motion of the UAVs. Okay, so here are some examples. I will quickly introduce them. This is the overall architecture of the research. So we have the input, the video image input. So detect the vehicle, trajectory construction, coordinate transformation, trajectory denoising. So 4 types. Of these 4 types, we will have the data. This is the training part. So we trained the YOLO V3 and V4 with our data, right? We actually manually marked those vehicles in the picture. Okay, so this is the first step. The second step, in this step, we actually did some enhancement learning for the dark vehicles and large vehicles because the sample is not large, so the detection rate is not good. So we trying to collect some more data. Okay, we manually marked those kind of vehicles for enhancement. Then finally, those vehicles can be detected. And also, there are a lot of challenge in this detection because the vehicles cannot be 100% detected due to a lot of factors such as the occlusion, the marking on the road, okay, and also sometimes purely due to the weather conditions, sunlight impact, something like that. So how can we transfer the detection box into trajectory? That's a challenge. That's a challenge. So we have some proposed some method, the deal with the ghost trajectory. Actually, it's not a trajectory, but it is detected. Disrupted trajectory. Okay, this is a trajectory, but we miss some data in between this start and end point. Repetitive trajectory. Okay, so we have different methods like the matching, switching, completion, elimination, duplication. Okay, so to actually try to link the trajectory, those trajectory together. Finally, we perform the denoising algorithm. Okay, so trying to eliminate the outliers and get the accurate trajectory data. You see, after the denoising, the trajectory is much smooth, close to the ground field data. So this is another kind of research. We use actually different research logic. Okay, so in this one, actually we draw a box for the detection. once the vehicle is detected in this zone, it will be tracked by the kernelized correlation filter, KCF method. Okay, so detect and track. The tracking is good, but it is affected by the detection. Okay, so this is the trajectory data we get from this method. And also we performed some analysis because the drone always shaking and moving, so we want to get those data in such conditions. Okay, so the drone have different degree of freedom camera movement. Okay, so the critical part is to do the background stabilization. How can you stabilize the background in the moving the scenario? Okay, so that's what we do. We use a temporally robust global motion composition method, okay, to stabilize the background. So this is actually the video in the PowerPoint, but it's in the PDF, so we cannot perform the video. But I will introduce this drone is flying along the road with a lot of change in the shooting direction. Then this is a stabilized picture. Okay, so we can actually accurately detect and track those vehicles and get their data. Okay, here are some examples. We then actually set up a website after we get some data. We think the data is good for researchers, so we built a website. We put some good data, I think, for research purpose. So less than one year, so I see a lot of visit for this website. So you see we have the data download part. We have the research, share the new research in this area. Okay, that's some data we have. You see, this is different from the NGSIM data because we have the free flow data and the congestion data and the state transition data. In the NGSIM, you only have the congestion data. If you want to analyze other phase, you don't have such data. Okay, so that's finally we can conduct the research because we don't limit it by the data. Also, my friend developed a software platform to help other researchers to extract this data. But it's not online yet. I think they will finish it in about 1 month. Okay, so this is the data. Here are some published work in the trajectory data collection part. Okay. Okay, so now let's go to the third part. So now we have the data. We have any trajectory data in anywhere you want. So what kind of research you can do? So for the traffic operation research, I think it's very interesting because you have a lot of complex traffic phenomena on the freeway. You want to know why, right? Before you have the trajectory data, you only can analyze the feature. You don't know the cause. Now we can know the cause. So the first, so this is our focused research topics because we only have limited effort and limited number of students, so we can only focus on some topics. Now, here are some topics we want to conduct, underlying the reasons behind the phenomenon of capacity drop. Okay, linking bottleneck driving behavior and microscopic traffic flow features. Investigating the mechanisms through which individual vehicle affect the traffic flow. Okay, I think those microscopic analysis can provide insights for the CAV control. So we are actually conducting the research at the same time. Once we know how this traffic problem happened from the trajectory level perspective, then we do the simulation analysis using the CVV technology to solve those problems. Okay, you know why this happened, you know how to control it. If you don't know why the congestion happened, you don't know how to control it, right? So this is the first research, we focused on the capacity drop. Why capacity drop? Because of two reasons. The first reason is that when before I left Berkeley, I have several months, I talked to Ku Hongchun. He said capacity drop is really important. I want you to analyze it with the detected data. So I spent like a lot of effort on this kind of research. But then I came back to China. I don't continue this capacity drop research, but I know it's important. And the second reason is that the Michael Cassidy, he has a very great article, this one. I highly recommend you to read it. It's very short, but I think he explains everything like in the traffic congestion in this article. The capacity drop is actually the core issue of congestion and the fundamental reason for the effectiveness of traffic control strategies. So if you want to use the traffic control to solve the congestion problem, the first thing you need to know is the capacity drop there. You see, when I was in Berkeley, I read a lot of articles. We have very famous researchers in the traffic control area, like the Papa Jujers, he's very famous in the control part, but he doesn't take a lot of effort in capacity drop. Then I see Cassidy write a lot of articles explaining why capacity drop is so important, why your research is not good, it's wrong, your theory is wrong. Then you see, because he's stating the fact, so I think in the following the research, the Papa Jujers fully take his advice by considering the capacity drop. But why capacity drop happen? That's important, right? So this is the standard method, the cumulative flow curve to find out the capacity drop magnitude. It's between 10% to 30%. What does it mean? It means if there's no congestion, you can see the flow rate can be to, let's see, 3,000. But when this congestion starts here, you see the flow can drop to 2,000. 1,000 capacity just disappear. Okay, so that's the capacity drop. So this is another good research article if you want to look into the capacity drop. This article explains the theory about capacity drop. But so people know how to identify, how to quantify the capacity drop, there's still some remaining issues. For example, someone believes it is caused by stop and go traffic. Someone believes it's caused by lane change. Someone believes it's caused by the driver behavior. Okay. However, they only have the assumptions. They don't have the real data to support their conclusion, right? So that's why we conduct such research. So the first research I conducted, actually, I take the video at this active bottleneck. Downstream is free flowing, upstream is congested. We take the video covering the traffic start from a free flow state, include a capacity drop, and ends with a congested flow state. Okay, so we have the video, we extract the trajectory data. Now we can do the analysis. So first we draw the picture, we draw the cumulative curve, trying to identify the location and the time of the capacity drop, right? This is the standard part. Then we have some microscopic data. So we then do some exploration. So we find out the capacity drop actually correlated with lane change. Okay, when the lane change number peaked at 36, the capacity drop happened. So I think then we go back to check these articles. They have several good articles to check their theories, assumptions. Okay, so I think we just follow their assumptions, trying to validate it with the empirical data. So you see, this is the validation work. So for a standard lane change, actually it has the anticipation part and the relaxation part. Anticipation means before the lane change, the preparation part. Relaxation is after the lane change, okay? So this is the two-stage, okay? Two-stage. Then you see different line change maneuver actually have different impact on the following vehicle. So if you check the research, so they have a lot of research, good research, trying to analyze how different driving lane change maneuvers affect the following vehicle. You see, different kind of gap, the distance, okay, they will cause different behavior of the following vehicle. So this one, the lane change have no impact on the following vehicle. This one, the lane change forced the following vehicle to full stop and then accelerate, right? So they have different impact, okay? So this is the summarization of the research variables focused on the capacity drop, lane change impact on capacity drop. Now we come to the core part. You see, in the lane change, actually we want to know the headway because headway is reciprocal of the flow, right? The headway, 1 divided by headway is the flow. So actually we can, flow is related to the capacity and capacity drop. So actually we managing the headway so we can know what happened. So here are 4 parameters related to the headway. This is before the lane change. You see, if this vehicle want to get in, before he fully get in, this vehicle will decelerate and create a longer distance or a shorter distance if I don't want you to get in. Okay, so that's the first change related to the lane change. That's the first change in the headway related to the lane change. The second and third parameter is after the changing lanes. Okay, the headway between the lane changer and the preceding and the following vehicle will change. So that means, so you finally get in. You see, this headway will change. Maybe become larger, maybe become smaller because the lane changer need to adjust his behavior, right? And this one, this headway will change. After this vehicle get in, so the following vehicle need to adjust the headway between with this one, right? Maybe become larger or smaller, okay? So this is the headway change in the original lane, right? So when this vehicle move away, the distance between these two vehicles will change. Actually, when he left, there's a gap here. The following vehicle can keep a smaller gap with the leading vehicle. Okay, so now we know here are 4 headways related to the lane change. Then we can calculate. We can draw their curve, calculate how they impact the capacity. Actually, here are some initial work. So for this one, this HLCV, it means the changing vehicle with its following vehicle. It goes to the peak at the capacity drop time. This one is a headway related to the following vehicle, okay? So it also go to the peak during the capacity drop. And for this one, the headway before lane change, okay, you don't see obvious increase, but after that, after capacity drop, you see a sudden increase. And this one, the headway in the original lane, you don't see a sudden change, but you see its value is negative. It's negative. So we sum all those headways together. You see, finally we have a summarized headway related to the capacity drop. So you can see why there's capacity drop because a lot of lane change occur at the same time. They cause the increase of the headway. That's why the capacity dropped. Okay. And here are some findings. The traffic is flowing, lane change behavior has minimum impact. But when the cumulative impact of lane changing has rapid increase, when the impact reaches the maximum value, it results in a dramatic reduction in the capacity. Okay. Also, we conduct some analysis to see the location of those variables, variable change, headway change. Okay. So I think with this kind of research now, we see why there's a sudden drop in the capacity and how can we prevent it. Okay, so we have different database. We actually collect a lot of data. We validated those findings, and we see they have the consistency of the findings, right? And then we then we want to know. So what are the traffic parameters actually affecting those headway change? Then we conduct the statistical analysis. We have some research findings. For example, like this one. After entering the target lane, the smaller headway and the larger speed differential are more likely to create larger gaps, which means if the initial headway is small, if the speed differential is small, is large, after the lane change, the headway increase will become larger because vehicles need to respond to those sudden change in the traffic. Okay. Actually, we can actually predict and analyze how those traffic factors affect the lane change factors. Now if we change the vehicles to be the CAV vehicles, the autonomous and connected driving vehicles, now we know how to control them, right? We just control those parameters, not let those parameters reach the capacity, like the capacity drop criteria. I think simply saying those vehicles don't change lanes at the same time. Okay, you can change lanes at different times, so we can still make you change lane, but doesn't cause a dramatic impact on the traffic, right? So that's the research logic. That's the research logic. Okay, so that's another research based on the trajectory data. Then, if you look into the literature, you will find out some researchers trying to explore why how driver behavior change before and after the traffic congestion. Okay, so this is the standard the Univ car following model. Okay, it has two parameters: reaction time and the jam spacing. Okay. You see, this is the reference. The reference. If it is if Univ car following model is correct, the follower will exactly follow the leader in this trajectory. But if we see the actual trajectory, it is different from the Univ trajectory. So that's why we need to explore how it means the driver characteristics is changed. We want to know what is changed. Okay, so that's why we conduct such research. Okay, so this is we follow the research, the assumptions in the previous research. You see, we have several parameters that can describe the driver behavior. Some driver can be classified as timid. Some driver can be classified as aggressive. Some can be recognized as no clear pattern. Okay, so if you are measuring the parameters, in the traffic, in the trajectory, actually you can measuring the change in the driver behavior. So you see, this is from the previous theory. So they have the convex curve. Concave triangle pattern. This one, the convex triangle pattern. Different pattern, they mean different driver behavior. Okay, so the concave pattern means driver is tend to get like farther to the leader, okay? Which means it is timid because you keep a larger gap. You want to be away from your leading vehicle, okay? Then we calculated the parameters for every every vehicle, okay? So then we summarize like these characteristics. You see, we have some interesting findings. Before the vehicles encountering the oscillation, the shock wave, the kinemagnetic wave, you see, we see half of the drivers are originally aggressive. You know, it's in China, you see drivers are aggressive, more aggressive than the US. Half of the drivers are aggressive because they keep a close headway. Only a small part of the vehicles are like no clear pattern. You know, the timid driver is more than 30%. After they encounter the oscillation, you can see the later aggressive the proportion is smaller. The later timid is smaller. You see, this part will increase. Okay, so it means like the driver behavior is significantly changed in the traffic flow. It's not just keep the same. Okay, so that's also some important. If you want to see why there's congestion happen, why when there's congestion, it is difficult like to dissipate, right? Because driver behavior is changed. And those driver behavior is related to their, I think, psychological part. You see, they change their behavior. So that's why it is different, fully different. Okay, so we compared our data in China with those from the US. We see very interesting findings. You see, in the US, only 30% of the drivers are aggressive, but we have 40%, right? Okay, almost half of the drivers are only about 20 to 25% are timid. Now we have 30% are timid because, you know, some cars in China, you know, it's not good. You know, some cars are full of goods, right? So they don't want to drive aggressive. Also, this is the change before and after encountering the oscillation. It's different in the US. It's different from in the US. You see, while in China, while in the United States, after encountering the oscillation, the majority of the driver will become will not be aggressive anymore. But while in China, you see it's concave, this one, concave, this one. Okay, so we only have a small proportion of the drivers, you know, will no longer be aggressive, which means even encountering the oscillation, Chinese drivers are still want to keep aggressive. You see, I don't know the driving style here, but if you drive in China, you will see aggressive driving a lot. Okay, so here are some interesting findings. Why we have different patterns in the traffic in China and in the US? Why the traffic patterns are different? Because the driver behavior is different. Driver's reaction is different. You see, so we can explain a lot of traffic phenomena. Also, if you have interest, you can go deeper. You see, you can explore the acceleration curve, deceleration curve for each driver to see how they perform, how they react. You see, those are some research we conducted, but I think it's too complicated, and my English is not that good to explain this to you. So I will just jump it. Okay, so this is the trajectory level traffic operation research. So we do see with this kind of new data at any time, at any location, so we can do a lot of things. We are actually doing a lot of things, but I still see a lot of research opportunities. So if you have interest, I think you may focus on those. Do you have questions or no question? Okay.
Yeah,
Oh.
Is aggressive good for diminishing headway? If people are aggressive, they are following close to the front vehicle, then they increase the capacity. Is it true?
I think if you keep a closer headway, the capacity will be higher. But I think it is vulnerable because if you have some like disturbance, it will have the falling impact is larger than those. If you keep a large distance with the leading vehicle. Okay.
And also, will a smaller headway in general increase the to make the traffic stream more vulnerable to the disturbance?
Yeah. Yes.
Yeah, so the capacity will increase, but it will be more vulnerable.
Yes. So if you read some research articles based on the Chinese data, like the Sun Jian from the Tongji University, he had a lot of publications. He found out a phenomenon. The capacity on the expressway in Shanghai is totally different with the fundamental diagram is totally different from those in the US. So I don't remember exactly the details, but I think if you have interest, you can check how the traffic is different, like in China with the other country, with the United States. Okay. So I think I will quickly go over the safety research, stuff. Okay, so now we have the trajectory data, so we can do a lot of things. We did some research, but now those three topics we are currently actually doing. So we don't have solid results, but we are getting there. So I give you, with this data, you can evaluate the effectiveness of the surrogate safety measure. You see, now we have the TTC SDI as a surrogate safety measure, but it's not so good if you have the data to validate it. We can develop new surrogate safety indicators for better performance, and also we can analyze traffic safety from the microscopic trajectory data. Okay. So that's the traffic safety analysis. The traditional safety analysis based on the statistical data, accumulated in 3 years, 5 years. So you develop the crash models, okay, trying to get the impact of variables. You see, then with the traffic loop detector data, aggregated data, then you can see you can conduct the traffic safety analysis based on the trajectory level. Okay, so that's some data you have. Well, in the California Sweaters database, you can see you have more than 100 variables for you to develop your model. So, while in the real time, like the traffic safety analysis, so we have the aggregated data supported analysis and the trajectory data supported analysis. Okay, so here's some research we conducted. So those are the TTC. I think you're all familiar with the TTC. It's a safety indicator. The TTC can reflect the safety performance. Now some other SDI index, some other index still can represent the safety. Okay. So, but I will explain. So what we currently doing is we fly the Zhong. We have a large research group. We ask the students to fly the Zhong. We actually collect 30 crash. We have the trajectory data before and after the crash. We have the trajectory data. So now we also have, I think, more than 60 days.
Which means your students fly the drones and keep waiting for the accident.
Yeah. Yes. Actually, we have some expressways which usually have accidents a lot. So we just staying there and capturing. Yeah, so we have 30 crash data. We have like more than 60 days without crash. So we just fly 1 hour per day to collect the data. So now we have actually the trajectory data with crash and without crash. With this kind of data, we can validate the surrogate safety measure. I think if you read the research articles, they have several methods to validate the surrogate safety measure, but they don't have the trajectory data with the crash. So if you have the data, you can directly, validate your surrogate safety measure. You see, they also in the previous research, they linked the surrogate safety measure with the crash data in the whole region in the 3-year long period. Now we have the safety indicator and the crash data, so we can do the direct research. Also, we are trying to incorporate different parameters within the surrogate safety measure, trying to improve the performance. Actually, we find out if we integrate the magnitude of the oscillation within this TDC, the predicting performance will greatly increase. But I don't put those results here. Sorry.
I have a technical question. So how do you observe all accidents in every intersection in the city? If you use 100 drones or 1,000 drones, how do you do it?
Actually, we only monitoring it at one location. Just one location. Yeah, we repeat the operations. Yeah. Okay. Also, here are some research with publications. So I think I put it here. If you have questions, you may read those articles for clarification. Okay, so then we conduct the safety analysis based on the trajectory data. The logic is we want to see the impact of the lane change from the trajectory perspective, how it affects the safety, how it affects the capacity, okay? So we conduct the research. Here we actually have a lot of variables. You see, we developed some equations to calculate the impact of lane change on the capacity and on the safety, okay? We actually use the TTC and TTC series as the safety indicator. So I think we have different interesting findings after we do the safety analysis with the trajectory data, okay? So factors such as vehicle spacing, speed differential, speed acceleration influence the lane change safety. Also, we have some other results like motorcycles frequently engage in aggressive lane change, which can increase flow, but also lead to traffic conflicts. Now, this is the motorcycle. The flow change. The motorcycle will increase the flow, but it also increase the TIT. The larger means more danger, okay? On average, passenger car has the highest level of safety during the lane change. Automobile, the safety is the best, okay? Safety is best. Because we have the trajectory, we can actually calculate the vehicle speed and the vehicle acceleration rate, trying to see how these two parameters affect the safety in the trajectory. This is another research analysis of relationship between three-phase traffic flow states and safety risks. Actually, in our research, the bigger research group, I collaborate with another professors called Chengcheng Xu and Pan Liu. We are the research team. We write an article trying to analyze the safety in the three-phase traffic stage with the loop detector data. We have the detector data, we have the crash data, aggregated data. We read an article published in the Accident Analysis and Prevention. So that's, I think, important research outcome in the three-phase traffic flow theory, the safety from the safety perspective. Now we have the trajectory data. Then we conduct a similar analysis, trying to see how the safety performs in three-phase traffic flow theory with the trajectory data, and we compare it with loop detector aggregated data. Okay, so we use circuit safety measure as the indicator. You see, we conduct the safety evaluation. It is a little bit complex. We conduct the safety evaluation. You see, this is the flow. This is the density. Actually, this is the fundamental diagram in different scales. See, this is safety. The color is safety performance. So you can see clear difference. This one is always related to the the safety issues. You know, this is relatively safe, right? You see, from this perspective, you can see the difference. It's more operands. They are clustered into different groups. Oh, it's okay because I deleted a lot of results because I was told the presentation is 1 hour. Okay, let's go to the the summary and the future perspective. You see, in this presentation, basically I revealed my research story in the past 5 to 10 years. How I step by step find out new research opportunities, how I conduct some research, and how I find some new conclusions. So I think whole sample trajectory data can provide a more detailed data source for traffic analysis. It enables the revelation of traffic patterns from a microscopic perspective and the analysis of the causes of traffic issues. Based on the trajectory data, it is possible to reconstruct the traffic flow series and methodologies for the traffic safety analysis. We are still doing the research with the trajectory data. And if we look into the future, I think we can do several things. Validate traffic flow theory models from microscopic trajectory level and the development of aggregated and new models. So if you read traffic flow theory, you see a microscopic traffic flow theory. They have a lot of research articles with a lot of assumptions. Are those assumptions right? Can we validate it with the empirical data? Can we upgrade or can we develop new models to better explain the microscopic traffic? I think those are opportunities. The model aims to uncover underlying causes of traffic congestion and the safety issues and propose control methods. Okay, with the trajectory data, we know how congestion and crash happen. And then we can use those new findings to support the control method, okay, of the connected vehicles. The combination of real trajectory and the driving simulators allow for analysis and the evaluation of those factors. I think with the driving simulator, we can create actually very a diverse environment and scenarios. For example, so we can test different technologies in the connected vehicle or in the connected environment. You see, and how congestion happen and how to trying to do some control. We can with driving simulator we can create different environments. You see, I think with that kind of experiment, so you can have new findings, because in the reality we don't have connected vehicle environment, but we can do it in the simulator. We can then combine it with the trajectory data analysis method. I think new results will come. Okay, that's my that's a share of some of my research ideas. Thank you for this opportunity. It's really beautiful in Jeju. Thank you.
Do you guys have any questions?
Don't ask tough questions because you have not graduated. It will affect your graduation performance.
Thank you for your talk about how we collected traffic data and using that based on the data, what we can do for our research. I just want to ask you about what do you think about the data collected from the driving simulator and what we need to consider to build a virtual environment to collect the realistic data from the driving simulator? Because I think the using drone is the most actual ways to get realistic data, but sometimes it has a limitation, like the shade from the blind spot due to vegetation, or it's pretty hard to capture the specific event on the road, like an accident. So what do you think about the data from the driving simulator?
Yeah, I think driving simulator is a very good technology to create the data, right? Because if you are running the simulation analysis, you actually have the trajectory data for every vehicle, right? So you can create a lot of specific environment to do analysis. I think before you do that, I think you can carefully calibrate your simulation environment to make sure the simulation is consistent with reality. You see, for example, if you want to do some analysis, I think you can collect a small kind of trajectory data. You can calibrate it. You can reproduce the traffic phenomena in the simulator. Then I think you can use the simulator to do some tests. So I think that's one part. The second part is in the simulator, you can actually create some environment that are not feasible in the reality. For example, you can send a message. You can send a message to the vehicles. From the infrastructure perspective, you can test how the intelligent vehicle perform, how the normal driving vehicle perform within this kind of environment in the simulator. I think simulator has a huge potential. I actually have some students trying to do some research in the simulator. So, yeah, but I think the research perspective is microscopic, the trajectory level. I think that can help us have some new research ideas. Okay.
So thank you for a great presentation, and then I think especially for the student, it's a great summary about how this entire domain is evolving, like starting from using the aggregate data to the more detailed trajectory data, and then how the methodology is also evolving from the more traditional probability-based model to the other type of model, including how you use deep learning to extract the trajectory and so on. So I think we all learn a lot, and then I really appreciate your presentation. I just have a very general question about, you mentioned there are several factors that could cause the capacity drop, like including the stop and go wave, and also maybe constant lane changing or unexpected human driver behavior, and then there are also many studies in this area. So I'm just curious about, do you think it's important to also study the interaction between these different type of factors, so let's say we study the stop and go wave plus the lane changing together. So do you think it's worthwhile to investigate this type of interaction? Or is there any existing study that already investigated this?
I think definitely it is worth to do such investigation, because actually what I present here is some straightforward part of the methodology. We have some complex part, developing some more complex models and do some deeper correlation analysis between the traffic flow status, the driving behaviors, and the change of the driving characteristics. I think that's a lot of work. actually, we only have 2 PhD students focusing on this research area because we only have 1 PhD per year. So a lot of work still ongoing. I do see we find some interesting findings, but there are still a lot of things for us to explore. So how can we get the whole picture about the capacity job is still unsolving task. So I think that's also why. So that's also so how we can perform the control in the future. So if we don't solve the cause of the capacity job, I think we cannot solve it in by the other technologies. Right? Okay. Thank you. Okay.
Thank you for your presentation. I think if we could get all the trajectories in the city level, that's gonna be really great. Like if you want to validate like traffic demand modelings, like as of now, as far as I know, there's no definite validation tool to evaluate your demand modeling or such things, right? So I believe investigating on the trajectory is very important, but I think it's a very detailed information. So it's like a lot of researchers are trying to generalize the trajectories that are coming from the real data. But also it is important to consider the human factors. Like every individual's driving behavior is different, right? So if you are just generalizing all that, and that's gonna be somehow output of an like generalized like data. So it's not. I believe it's not all the sophisticated information will be lost during the transition pre-processing the like process. So I know that also that a lot of people are trying to predict the trajectories that they have from the existing data, like NG, SIM data, those kind of things. So what do you think is the best way to predict the trajectories based on deep learning models or like machine learning models? Because like if you consider it in a large scale city data, then that's gonna be like computationally almost impossible at the current state, I believe. So what would be the best way to investigate on predicting those data?
Predict the trajectories.
Yes.
In the city level?
Yeah.
Okay. So I think that's 2 questions for me. I think for one question, how can you actually predict the trajectory, right? I think you're right, the trajectory is related to a lot of factors, not only the traffic factors, but also his personalities, right? So different kind of person, they have different kind of trajectories. So if you don't consider the personality, you will lose a lot of information. Actually, in our research, based on the empirical data, we have no way to get the personal information. We have no way to do the survey, look at your driver information, right? So that's why we can only do some analysis based on the general analysis. But in the driving simulator environment, we do count in the personality of the drivers. We actually measure different types of driver, measure his performance, and trying to link those performance with his the personal characteristics. I think that will together personal factors together with the traffic factors, you can accurately predict the trajectory of a vehicle on a specific road in a specific environment. Okay, so for the city level, it's really difficult to get the data, right? I know some research, they actually fly drones together, they collect all the trajectory data for a whole small region. So I think with that kind of data, you may do some city level analysis, but that's very costly, and I'm not sure. So such kind of data can be supported by the project. So if you have interest, you can search the website called a company called Data from Sky. Then you check his. He has shared his projects. So I think one of his projects, some people ask him to ask this company to extract the data for city level, like the UAV like videos. So, but I don't think that data you can get such data. You may write an email to see if you can get such data. Okay.
Yep. Thank you. Thank you for the fascinating talk. I really enjoyed it. I just have a couple of questions about data collection. So the first question, I think echoing I forgot his name, but this student's question is actually about, and have you considered like combining the data from the speed camera? Because speed camera capture the car plate number every time the car passes. And then you can just connect with the car plate with the individual information, which actually kind of contains a lot of different types of personal information. So for example, gender, income, stuff like that. So have you talked with any government to kind of connect or combine this speed camera data set with your drone data set? So that's my first question. My second question is, so I think it's quite challenging to use drone every time you have to kind of collect all the trajectory data set. You have to fly your drone every time, and actually you can just capture those kind of trajectory only short amount of time. So what would be the kind of like better way, I would say, alternative to capture all this trajectory data set in the future? I would say, for example, I think Xiaobo came down here to talk about the flying drone to deliver the package. So you probably can use a camera. You can just install the camera on the flying drone and then capture all these trajectories of the vehicles. So I'm just wondering, how would you see in the future, what future holds? So that's my question.
Okay, thank you. So you're right. If we have the speed camera data, so we will have a lot of information. For example, we have the vehicle type, we have the fuel status, like the emission, the performance of the vehicle. We will have the driver information, things like that, and we probably will get how many person are in the car, right? We try talk with the police agency because such data are within the public security department. So you don't share any data with the public. So even with the researchers, they see those data as highly classified data. They don't give that data to you. So we maybe in some a small experiment area, maybe we can have such data, but we don't have the trajectory data. So you're right. So if in the future, if we can have the speed camera data with the trajectory data, so we can perform some deeper analysis. The second is how to collect have a better way to collect the data. I think increasing the battery capacity may be one way, because for the normal people, you see the battery is limited to 30 minutes. But you see for the delivery purpose, maybe the battery will be higher, like 1 hour, 2 hours. I think if the delivery company share the video with us, maybe we can have get some data with their drones. But I'm not sure if they are taking the traffic when they fly in the drone. And also in the future, we are trying to have some other methods to get the trajectory data. In some freeways and urban areas, we are installing cameras together with the radar. So we have the radar data, we have the camera data. So I think that's another type of trajectory data, and I think that's can be large, can be like a cover a large area, right? But we still have some challenge in such data. You see the radar data, the speed is accurate, but the trajectory is not accurate at all, especially when the vehicles are suffering from the stop. You see the trajectories are like a mess. Also from the camera video from on the roadside, like you see you need to do the to the coordinate transformation, especially those vehicles far away from the camera, its location is not accurate at all. So that's some challenge we are encountering. I think if we can combine the camera data with the radar data, we may have a good trajectory for analysis. But I think it's still a lot of data processing work to do. That may be the future, because we do see the government is installing camera and the radar on the freeways, on the urban roads. Okay.
Thank you.
Thank you for your great presentations. Actually, I get to know what kind of factors causes a capacity drop, road capacity drop, and I guess if we can control those kind of factors, like reducing the frequency of lane changing or the preventing the bottleneck situation ahead, the road capacity will be better. So, what do you think of the best way to control those kind of factors for preventing capacity drop?
Okay, so I think the traditional way to prevent the capacity drop is to measuring the density at the capacity drop location, and you control the density, then you control the capacity drop. That's based on the findings, the capacity drop findings based on the aggregated loop detector data. But now we see the capacity drop is not happened on road section. It's actually the accumulation of the driving behaviors within a short section, right? So I think control the density is maybe a good way, but we want to control the driver behavior in a more fine way, right? So how to control is highly related to the reason causing the capacity drop. Based on our current research, I think we can control the lane change. We can control the lane change time of all the vehicles, coordinate the lane change behaviors, and monitoring those parameters. For those vehicles who change lane will have a very large impact. We may temporarily control this kind of vehicle lane change. We may ask the drivers to cooperate, create a better environment for this vehicle to change lane, to reduce its impact on the whole traffic. So I think that's maybe the way. So we can test it in the connected vehicle environment.
Thank you.
Well, yeah, thank you for the talk. Well, I was very interested in your presentation because I personally on the area of this kind of research. So I have so many technical questions, but I just want to ask
really?
one thing. Well, I've been done those kind of analyzing the NG sim trajectories and some other trajectories even in Europe, but because my purpose was to find out how can we define the aggressiveness level of vehicles so that finally we can model it in a simulation. So first time I tried was I focused on the longitudinal behavior like abrupt acceleration and deceleration or something like that. But some point I rather think the lane maybe aggressive lane changer is really aggressive driver because acceleration and deceleration is actually are made by the situation, because if it's danger, the people anyway has to be sudden stop, right? But the lane changer is solely by driver's characteristics and their personality. But I'm still thinking, well, so what is really a driver aggressiveness level? And how can we define that the driving aggressiveness based on parameters, and what kind of parameters we can use it, and what kind of parameters we can use it for modeling more autonomous vehicle, like aggressive or less aggressive or non-aggressive or something like that. So I was just wondering your thought and then your experience or something.
Okay, I think yes, aggressiveness is very important in the traffic analysis, because we in the literature, researchers do find out aggressive driving will have a large impact on the traffic, causing the congestion and the safety issues. I think to measure the aggressiveness, we may have a series of factors, such as as you say, acceleration rate, deceleration rate, and also I think the headway you keep with the following vehicle, and also the lane change opportunity you choose to perform the lane change. So based on the empirical data, we do find out a lot of aggressive lane change. We find out some lane change are so aggressive, the gap between the lane changer and the following vehicle in the target lane is negative, which means so the space is not enough for one vehicle, but this vehicle just cut in, have a large impact on the traffic, because the following vehicle need to decelerate suddenly and to a full stop to prevent the collision, and the lane changer will reduce its speed, okay, and fully decelerate, and then have an impact on its original lane. So this kind of aggressive lane change.
Smaller gap in lane, so smaller gap during lane change is aggressive, and then large gap during lane change, that's non-aggressive.
Yeah, I think so. And also based on the theory I introduced, they have two parameters actually. One is the distance you keep. The second is reaction time. So do you react fast with the change of the environment, or do you react slower with the environment? So actually I see people use these two parameters to describe the person driving parameters.
Okay.
More questions? I have one
Oh.
different from your research,
Oh,
but yeah, I wanted to give our students some tips.
okay.
You published more than 100 papers. Okay, you've got more than 5,000 citations. Do you remember which paper that is the most attracted by other researchers among your paper? And can you give us a tip how you attract citations?
Good. So I think the most attractive one, I think we have some, when I have a new idea, I think the first paper is the most attractive one. So actually before, when I get the PAMS data, the loop detector data, I actually trying to find out how can we predict, how can we link the traffic with the crash, with the safety.
Okay.
So I actually spend a lot of time doing the data collection analysis. I talked a lot with Kuhn and KAIST, and asked a lot of questions with Kitty, and finally I have this first paper published.
Do you remember which journal it is?
It's in the Accident Analysis and Prevention.
Okay.
Yes. So I think that's set up a foundation for my following vehicle based on the detected data.
Nice.
Then I have the first one when we achieved the data collection from the UAV videos. I think that's important one. The citation is also good. citation is also good.
So why do you think those two papers got a lot of citations? I think that's the important for our students.
I think the scholars and the researchers, they are like seeking for solving the same problem. So if you have a good idea and you actually solved some problem they have, I think they will like read your article following the research idea. I think that's why they really can have get some insights, get some like ideas from reading your paper. So if your research paper can give him some insights, I think they will cite your article. Actually, I'm don't pay a lot of attention on my citation.
But you still have 5,000.
I think maybe we have a research group. You know, I have some colleagues like Cheng Xu. He also have a high citation. We usually collaborate with each
Work
other.
together. Okay.
Yes. So
Working
we have
together.
like several highly cited articles. So I contribute to his, he contribute to mine. That's why we have total citation is good.
Okay. All right. Yeah. Thank you very much. Anything else? If you don't have any questions anymore, let's let me go. Thank you. Thank you.
Yes. Thank you.